This week we gave an introduction to quantum physics using the many-path formulation of quantum mechanics. In classical physics, the system will go from one event to another using only one path, the classical path. In quantum physics, the system can follow all the paths. So each of the paths has a given action. And using this action, we can calculate the amplitude associated for the path. So and we show that it's exponential of I times the action divided by h bar. But because the particle can take all the paths, we have to sum over all these amplitudes. And that will give us an amplitude of probability, phi, to go from event A to event B. That's a complex number, but if we want to get the actual probability for going from A to B, then we take the modulus squared of the amplitude. One appealing aspect of this approach to quantum mechanics is that it's relatively easy to take the classical limit. So we recover classical physics, and in particular the stationary action principle, when we take systems for which the action is much greater than h bar, which is the case of classical systems. In that case, a small change of the path induces a large change of s divided by h bar, because h bar is a very small number. This means that when we sum over path, we sum over phasors which are in all directions. And we know that when we sum vectors, or phasors in this case, in all directions, the result is 0. So we always get an amplitude of probability which is 0, except when the action doesn't vary rapidly when we change the path, which is when we have a stationary action. In this case, all the phasors are more or less aligned, and that will be the only non-zero contribution to the total amplitude of probability to go from one event to another. And that's for the classical path. We also introduced semi-classical approximation, which is a way to do some practical application of the many-path formulation of quantum mechanics by keeping only part of the quantum physics. So what we do here is we only take, instead of summing over all the paths, we only take the most relevant paths. So for instance, when we have a two-slit experiment, we will take two constant velocity paths through each slit, and that's because these paths with constant velocity are classical paths. That's what we call the semi-classical approximation. But we still have more than one path, so when we sum the amplitude, which are complex numbers, we can see interferences, which is what we get when we have the actual experiment. When we send electrons through a double slit, we see a pattern of interferences. We see dark and black and white fringes on the screen. And that's what we will try to reproduce in the workshop using what we have learned of the many-path formulation of quantum mechanics with the semi-classical approximation.